particle. If the particle diffuses faster, it will lose memory very fast. If it diffuses slow, it takes time until it will lose memory. And another note about terminology, this process is also called the correct term is memoryless, even though I say that there is a memory, because mathematically it's memoryless, because once you know the process at one point, you don't have, you fully specify the process. So you lost all the memory. You don't need the memory of what happened before. So it's like the process forgot what happened before and say, now I'm at this value. I don't need to know anything else. That's why mathematically it's called the memoryless. But then in a more informal way, I use that word memory. But just in case this could be confusing. Yes, so in lay terms, yes. But from a mathematical point of view, just a mathematical language is called memoryless. Not because there is no memory, but because once you know the process at one point, you fully specify the process. You don't need to know the process before. So this may be confusing. I remember first time seeing that and reading the literature, and I was confused why it was called memoryless if there actually is a memory. But it's just a quick, just language issue. And the next plot, I show just an histogram. So as you remember before, we generated 1,000 random numbers and plot the histogram, and we get the bell shape. And the same thing we do here with much more random numbers. If we plot the histogram, we still get the Gaussian distribution. So it means that this is just another confirmation of the property. This is another statistical property of this process. I use norm PDF from SciPy stats to plot this. Okay. And having used the same sigma in the two cases, both for the process and the Gaussian line, I get the same width here. So this is a, you can see this plot, think about this plot as a kind of testing of our function. And this is actually one of the kind of optimization rules that I laid down before. Let's see if I can find that. Start with reference implementation, test reference implementation. And the next rule actually is, if performances are good enough, just stop. You don't need to optimize anything if you really don't need it. You're just wasting your time. Because it's cool to learn new techniques, and then next time you have a problem, you say, ah, yeah, I know how to optimize it. And then you want to optimize it, but it's a waste of time maybe, because it's already fast enough. So find a good problem first to optimize. Okay, so here, in the spirit of testing, I add some more test of normality. So we did just plots before. What I'm doing here, I generate the same plot as before, histogram and Gaussian curve, but I add the actual test. So a graphical test is fine, but you want a quantitative test, something that later on you can automate. And this can be done very easily in Python using assertion. Here I compute a score that's basically a chi-square. So it's the square root, the sum of the square of the distances between these two curves at each point. So it's kind of a chi-square. And I assert that this should be smaller than a threshold. The cool thing about Python is that you can use PyTest that accept just normal Python syntax using assert. So you can cut and paste this code, except for the plot, and then make it in a unit test using PyTest. So Yeah, this is unnormalized. It's just the chi-square. So yes, yeah, you can. The threshold, you mean at 0.2? Yeah, I just put it empirically. So I played with it, and I put 0.1, bam, error. Okay, so because I know that graphically it looks correct, so it's not the mathematical way to generate the threshold, but these are to a first order approximation of Gaussian distributed errors. So there is always a possibility that you get infinite error, right? So you can normalize taking the mean. You can. Yeah, you should normalize by the sigma. You take the mean, and you compute the reduced chi-square, basically. You also take into account the degree of freedom. So you reduce, it's not exactly the mean. So you don't divide by n, but n minus the degrees of freedom in the reduce. Yeah. So you can do also, if you need more statistical accuracy, you can do that. But in practice, if you don't need it, you can also do a simpler test. So you don't need to derive a theoretical limit for this threshold. Yeah, because this is a test that will not test, it will test only one property, right? If you get here something that has a totally different shape, or it has a sigma that is twice what it should be, then you will catch it. Okay? Then you will have a series of tests, each testing a different property. And what you can do is, basically you know that with the certain random numbers, you should get this. So you can even fix the seed and then compare not to the analytical one, but compare to this empirical curve. So you can do a test that is perfectly accurate. Oh, this F score is the F string that I mentioned before. So it's a new kind of strings that we have in Python 3.6, I think, or 3.5, and 6. And basically it's cool because you put a F before the string, and then between the curly brackets, you can put the name of any variable, and this will be printed there. And this, so if you put it just by itself, is this. So it will print the value of score. But normally here is not printed because if the assertion succeeds, it will not print the message. The assert works this way. You put a condition here, comma, error message. So this is a kind of an error message to say, in case it fails, it will tell you it failed because it wasn't smaller than 0.2, but was this value.
Just take out from the comma and run it once, and then put the F string again and run it again. To make it fail, like put the threshold lower. Like
Yeah, what I did before.
yeah, and then remove the.
So assertion error, and the message is just a number.
Yeah, but take out the end string to see what's the default.
This one?
No, like the whole thing out, like comma and everything out to see what's yeah.
Like that?
Exactly. So that's the default.
No, because these are random numbers. Sometimes it doesn't fail.
So if you don't have like the assertion error or anything, it doesn't tell you what happened.
Yeah.
So you can put a string afterwards.
Yeah. Thank you for the comment. So that's the example. If you remove the message here after the assert, you don't get any message when the code fails. And you can easily put something fancier. Yeah, there was score before. Let's try. Oh, yeah. But if you want to do this, so you can add a more meaningful message. It's easy to mix a string that you want to print with the numerical values. That's the advantage. But the cool thing is that it's not limited to name of the variables. You can put a Python expression there. So if you have an array, so we are diverging, but here you can print x. Okay, x is a big list, but you can do min x and print the min. And this will be embedded in min does not exist, so you need to do npmin. So you can put the min in an error message, and so you just type the min is like that, and it's really compact. And as with the other formats, you can add like specifiers for how many digits you want to put, like 2 digits after the comma, stuff like that. Yes. And I found it very useful, one, for interactive work like that, because you don't type twice the name of the variable. When you use format, you need to put keyword and the name of the variable, and you need to write the name inside the string. So you write 3 times, and here you write it only once. Yes. And many times you have more than one. And second is exactly in error messages that I find it's extremely useful, because assertion or when you raise, you want to know the context that gave you that error. So most of the times you want to print values of variables in that context of the error. And you can do it immediately there with a very short syntax without having super long lines, because you want to print 3 variables, 4 variables. Okay. So everybody likes F strings now? Okay, second test is for correlation. That fails, because these are random numbers. No. No, because yes, because these are not random numbers. So what I should have done here is setting the seed at the beginning of the cell, so I know that the random numbers will be reproducible from run to run. Instead, if I don't set the seed, I can get, here I'm testing that the correlation at the beginning needs to be very high, and I put a threshold of 0.9. So the first sample after 0.1 second should be very correlated with a tau of 1. So I put a threshold of 0.9, but sometimes you can go a little bit farther, so you have a correlation that is a little bit lower than 0.9, because you have an infinite range of value potentially. So to overcome this, you just set the seed here, and you know that if it passes 1, it will always pass it. Okay, so this is what I'm plotting here is, oh, I put the labels, but I forgot the legend. So let's put the legend. So the blue curve is the experimental correlation between samples, and the orange curve is just an exponential with the time constant tau. And we see that they agree. And the last test that I do is testing that the initial value is actually x0. Okay. Perfect. So let's move on. So after we test our implementation, we start benchmarking it. Assuming that it's too slow for us, we need to really generate this process high speed because we need to generate 10 terabytes of these numbers. So we start with the benchmark. I use here 1 million numbers as a number of step. First thing we do is measure how long it takes with the time it magic. Magics are magic commands in IPython notebooks or in IPython. These are special commands that start with %. These are not Python commands, are just an extension in IPython. So it's not even a general thing in Jupyter. So if you use a kernel for R, you will not have the same magic commands. But these are kind of infrastructure offered by Jupyter to define magic commands, and then the specific commands are implemented by the kernel. For IPython kernels, we have timeit. We have quite a few options. N and R define how many times the function is repeated for timing purposes, because you have always jitter, and so you want to execute it many times. But if it's already slow, like 5 seconds, I don't want to wait forever. So I just put N1, R1, so it will be executed only once, because this is already slow, I know, so I don't care to measure it accurately. And -O just gives the output. You can do it without -O and don't get any output in a variable like bit0. But I want to save it for later. So that's the meaning of this other option. So we see that it's 4.8 seconds on my laptop. So yeah, it's pretty slow because we want to generate it. We are in a finance group. We do very high frequency trading. We make money with speculation on the noise of stock prices, and we want to be fast in generating our predictive model. So 5 seconds, we lose all our money. I don't know what I'm talking about. Okay, the other benchmark command is prun. Prun will run for us. We'll use the module from the standard libraries that is called, how is it called? I forgot. Profile. It's called Profile, and there is another companion module that is called the cprofile that is faster. But anyway, prun will run it for us, and it will give the output just here in the notebook. It's a little bit slow, and it's not very easy to read because the screen is so small. But it gives many columns, and I explain them here. So basically for, let's see, okay, prun is a profile of a function. So you need to have a function. With timeit, you can time even expressions, whatever you want. With prun, you need to time a function, and it will profile every function call inside that function as well. So every function, there are, in this case, OU update that is called inside the OU process is called 1 million times. And its total execution times in this 1 million times is 4.2 seconds, and per call is almost 0. And the cumulative time is 4.9 seconds. So what's the difference between the total time and cumulative time? The difference is that cumulative time is the sum of the time spent in that function. Okay, total time is the sum of the time spent on that function minus the time spent in the sub-functions. So if I call, for example, the random number generator inside that function, which I do, and that is slow, I will see a total time that is small, but still a cumulative time that is large. In this case, I just want to go look at the implementation. Unfortunately, I cannot use the table of content. That is a super cool feature here because the screen is too small. But if you have it on your laptop, use the table of content to jump back and forth. Okay, so I guess we need to, you're fine. We start at 2, right? So it's already 50 minutes. Okay, so where is the implementation? Implementation, here. So you see that inside the OU update, we call the random, we call a rundan. So here, since these numbers are similar, means that we don't spend much time inside the rundan. So that is not the bottleneck of our execution. What we see here is that the bottleneck is all the rest. So, but we cannot actually see it directly because prun will profile function calls, not every single line. We wish we could profile every single line, right? Okay, so let's do that. There is a way to do it. And this is the next. Okay, and this line profiler is a cool package that you need to install, and then you need to load the extension, line profiler like that, and then you can do LP run with this syntax. You need to specify which function you want to profile, so you want to show statistics for this function, and then what you want to call. So I call OU process, but then I want to profile OU update because I know already that the most of the time is spent there. Also another point is that the total execution time was 5.6 and the call in OU update was 4.8. So actually the loop is not taking much time. It's OU update that takes most of the time here. So let's run this and close. Okay, so we get, it's hard to read, but we get we get a line-by-line benchmark. There are several columns, hits, time per hit, and percentage of time. You can just look at the percentage of time. So we see that 20% of the time is random number generation, 24 is this, 43 is this, and this is just 11%. Okay, so we want to optimize this too. Okay, perfect. So let's start optimization. First, I define the reference values. So I set the seed, and I generate the process. So then I can test that the optimized function will give exactly the same values as xref. And then exercise number 1, modify OU update 0 to do what? Of course, with the same signature. Okay, trying not to use NumPy because if you recall the implementation, let's go back. Here, we are dealing with scalar values, right? We pass one point and we get the next point. So all these variables here are scalars. And we are using this huge cannon that is NumPy just to kill a bird. So it's not worth it. If it's a scalar, we can use the functions, math function from the standard library, and will be much faster, a little bit faster. So try to modify it to not to use, what? You, yeah, just create a OU update 1. You call it 1, so you will not overwrite it. And you modify it, but not here in place. Just copy it there, in that point where we were. And don't run the next cell because we'll magically show you the solution. So then, where are we? Here. You add, oh no, I forgot the solution. I'm sorry. So don't look. I deleted it. I didn't see it. Yeah, because I did it this morning, adding this kind of exercise thing, and then I forgot to remove. Basically, when you run this, you load the solution. And then I forgot to remove it. And I save it with the solution inside. So that's all the game will not work. Anyway, don't look it and do it by yourself in 1 minute. And remove the green stickers while you're doing it and put it back when you're done. NumPy? Yes, there is a function for, there is a random module in the standard library for Python. And there is also a function to generate normal Gaussian distributed numbers, and it's called normal variate, I think. So you can try. The module is random, and the function is normal variate. You can do, you need to import it, and then you can do tab and complete random dot, hit tab, and series expansion? How? So you mean a linear approximation? Yes, but this will break if delta t is bigger. We want a solution that works with any delta t. We want the correct solution. Anyway, so the question was, can we use a Taylor expansion instead of using a square root and exponential? Sure, we can always do it, but these are quite optimized function, square root and exponential function. So changing them with the Taylor expansion, we lose accuracy, and we don't gain much in terms of performance, maybe a factor of 2 max. So. Mm-hmm. Okay, sorry. And now I got your question. So the question was the overhead that you add when you profile. That's true. When you profile, the code runs slower. But first, if we use time it, we get a pretty accurate measurement of the runtime because it's been designed to time it to use the another time it module from the standard library, and has been designed to have a very low overhead. So unless you are measuring microsecond or nanosecond execution times, you're good. And second, for profiling line by line or the other one of function by function, it will be slower, but we don't care because we always compare. If it takes 10 at the beginning, we want a factor of 100 reduction, for example. We know that we will reduce it by that factor. So it's relative to the starting point. But the absolute number, you can get it with time it. Asymptotically, it will scale. The execution time, it will scale in the same way, both profiling and not profiling. Because these are profiling tools, so they've been designed exactly for this purpose. Otherwise, they will not work. So another point that already came up two times. When you open the notebook, you need to set the kernel. So you need to go in the menu, kernel, and click on kernel, change kernel, and select the Pi 3.6 underscore optimize and kernel. Otherwise, you will not see all the packages that you installed. Questions? Okay, let's move on. Okay, let's say what I did here is just replace np dot with the math dot, and of course importing it. So let's see what's the result. Just in these two lines, I didn't change the random number generator. Just into these two lines, first I test the function. So this cell here sets the seed to 1, as I did at the beginning to create xref. Then I generated the numbers, and then I test that the two arrays are the same. And they are, otherwise I would have an error. Then I time it. And if you remember, it was around 5 seconds before. Let's see how long it takes now. Takes longer because I didn't put R1 and 1, so it's running it many times. So now is instead of 5, 1.3. So just abandoning NumPy that they told us that was fast, but actually is not if you use scalars. And here you see it's 7 runs. Okay, line profiling now. So we will use always the same pattern. We have the optimized function, and then we have 3 cells. Test, time, and profiling. So line profiling here says that, okay, this is not 40% anymore, but so now most of the time is spent in random number generation, actually. Has anybody tried to use the standard library random number generation? And? Right. So I don't recall from the top of my head if you can where you can set the seed. No, in principle, it should be the same algorithm. Is Mersenne Twister 19932 is a very standard one, but maybe the difference is not in the random number generator, because the Mersenne Twister generator will generate uniform random numbers between 0 and 1, and then you convert this to Gaussian distributed random numbers. Maybe that step is different. So the assertion fails in that case, but it should be working. You can test it with the other methods that we saw before. So the statistical property, test that the correlation is the same, test that the distribution is Gaussian. But what's the performance? It's worst. Okay, so I left the random number from NumPy because I know that is heavily optimized. Okay, let's move on. We're saying that at this point, the bottleneck from profiling is the random number generator with NumPy already. And the standard lib will not help us, it's even worse. So, but look at this function. We are calling for each time point, we are calling the random number generation. Instead of this, we can put this outside the loop and save time. So try to do it. And there is the solution here, so don't look at it. Just delete it.
You take it out, so it doesn't in fact generate all the numbers of one. No, it
So,
don't generate just one number.
is the question if you get the same random numbers? Is, okay, now I get your question. That's a very good question, because why you move the generation of the random number outside the loop? You do it only once, but you need to generate the same number of numbers, so what do you gain? You gain it because Python is slow. So every time you call a function in Python, you have a heavy overhead. So in this way, you call 1 million times the function inside the for loop. If you bring it outside, you call the function only once, and all the work is done inside NumPy that is implemented in C. Yes. No, you generate exactly the same exact random numbers. Yeah. I didn't want to give the answer. So yes, you need to generate all the numbers first, and you call NumPy only once. And then NumPy is implemented in C, so it will generate 1 million random numbers in one call of a C function, and it will be much faster. Sure. Okay, I don't see red stickers, so no. Okay, let's move on. Okay, I reload the solution here. So I redefine basically the function OU update, removing the random number part. And then I pass the random number as a parameter. And then I redefine OU process 0 as OU process 1. And this will not change the signature. So the difference is that now I generate all the random numbers here in one go. And then I pass one different random number. You see there is an index I at each iteration. Let's see how fast it is. First, we test it. So exactly the same. It's the same array as xref. So we didn't change anything to the algorithm, to the output. Then execution time, 1 second instead of 1.5, so okay. And this is the further profiling. Maybe Piran, let's see what it tells us. Piran tells us that calling this function is 30% of the time. No, this is the output of lprun, actually. So let's go line by line. Now we have 30, 30, 30. The 3 lines takes the same time. So it's kind of balanced execution time. And let's see. Yeah, that's what I was saying before about the replacing this expression with Taylor expansion, because actually if you sum two numbers or if you compute the exponential of two numbers, it will take almost the same time, because these are so heavily optimized in modern processors. Yes, but I don't recall. There are the sim optimization. I don't know if the processor have already these functions implemented inside. It's likely that modern processor, but as a matter of fact, this function will never give you much difference, even if you do it in C as a function of 50. Okay, so this needs to be some overhead involved with Python then. So actually, let's look at the code. The code is here. Here we call two functions in Python. So what the big, so the most of the time is spent calling a function actually. Okay, so we have call a function, and here we have a slow computation plus times that all happens in Python. Okay, there is no C code in this last line. So basically 30%, 30%, 30% is not because what you say that you're right, but it's because here we have overhead of function call, overhead of one function call, and this overhead is basically the same as summing these four numbers, and that's, so it makes sense now. Okay. Peer run. Let's see peer run. Peer run says that the cumulative time is equal to the total time. So actually calling, so most of the time is spent inside. So this is exactly a reflection of what I said, that the overhead of calling the function is assigned of on the caller function. So it spends most of the time calling functions and doing that operation. So let's move on and let's see how we can further optimize. So we can streamline the loop. Exercise number 3, please delete the solution. So streamline the loop. If you look at the implementation, there are these two variables, relax and diffuse, that we compute every time. And we have seen that actually it's not a computation that takes time, it's the function call that takes time. But they are the same at every cycle. There is nothing here that depends on the loop variable I. So we can move these two out of the loop, actually. So try to do that. So relax and diffuse only once. And I get rid of the inner function, it's just easier. So it will be only one function called the OU process 2. Okay, so we are running out of time. I think I should already show the solution. Okay, so I move the relax and diffuse here, and then there is the for loop. Okay, because these don't change. I was doing something really stupid, computing again and again, over and over the same numbers. So I just moved this out of the loop. We don't need a sub function anymore. It's small enough. And another trick that I use, instead of using normal NumPy arrays, I wrap them in a memory view. This is a pure Python trick. When you use an array element by element, the access of that array is pretty slow if you are using NumPy. But if you're using, for example, a list, accessing one element is much faster than accessing an element in a NumPy array. So the solution to this is wrap the array in a memory view object that is a Python object that you can access element by element. Will not have all the fancy features on NumPy like slicing and having all the methods, but for our purpose in which we use it element by element is good enough. Is not a list. So the cool thing about memory view is that it will reuse the same memory. So it's a view of the same memory, and you access it with other machinery that is faster than NumPy. So,
why did you name the bottle chain?
Because
better to do that one chain to see if the result was better one.
yeah.
Imagine the two effects. I can say now which one had the.
Right. You can do it by one. It's just for time purpose of this presentation. Basically, memory view. Memory view is gives almost negligible gain in this case because it's still slow. But since it's so easy, I just put it there just to show another technique. Yes.
Instead of looping with the index, could you faster loop over n norm? Would that be faster to?
Sorry, I can't hear you.
Instead of using the index and then indexing it, would it be faster to loop over n norm itself?
And norm is an array, so I don't have to use the full array. I need to use one element of that array.
Yeah, but you could put that in the for loop.
But that's going back to the first implementation that is slow. You generate one number every time because it's different every time. So we generate all this bunch of numbers and then we use it one by one in each iteration.
Yeah, but you could get rid of the index and the indexing operation on that.
Yeah, but that's it's so much slower to generate the numbers than you don't actually putting the index is not as slow as generating the random number.
I think what it means is that you write 4 element in n norm.
Oh no, yeah. So you say in the for loop you do a zip. You do an enumerate. So you don't need even I anymore. You just do, yes, you can do that, but you don't gain anything. No. Basically, Py is always Python accessing the memory view element by element. So either you do with the syntax using I, or you do with the iteration in the loop. It's almost negligible. Yeah, you can try it, but it's almost negligible.
How about using a DAC instead of using the memory view?
Using a DAC,
DAC, D-E-Q-U-E, it's optimized for copying and appending.
yeah, it's like using a list. It has the same time of accessing elements as a list. But the problem is that it's a completely different data structure. So if you generate 1 million numbers, you need to copy it in another data structure. And that's the problem. It will be slow. Instead, with the memory view, you reuse the same memory. You just wrap the same memory with a little bit of metadata that is the memory view. It's like a pointer. Yeah, yeah. Okay, so we got this, 10 minutes. Okay, and we got down to 200 milliseconds. Yes, but we saw it before that the append doesn't have much overhead if you go line by line, and you can actually put the append in a new line. So you see it by itself in the line profiler. You will see that the append is pretty fast. It's not super fast, but at this point, the other operations are still slower. So now at this point, yeah, that's actually the next step, getting rid of the append, but you will see that the difference is not so big. Okay, so what are the results? 300 milliseconds here, and before there were, I don't remember. I wrote here 2x improvement. So this trick of what? Putting these variables out of the loop and using a memory view gave some other improvement. Okay, so NumPy arrays are slow to access, and memory view can help. So the other exercise here will go faster now, is a new function with a NumPy instead of appending in a list, like that question that was brought up. So what I do here is I pre-allocate X. Instead of creating an empty list and then appending, I pre-allocate all the memory with a NumPy array. And then I use the memory view trick just to have a faster access. So memory view can be used in read and write. Also to fill this array, I can use a memory view, but just element by element. So the only thing that changed here is instead of the append, I just put X of I plus 1 equal the same expression as before. Okay, so let's see what's the result. Getting rid of the append. 258 and was 250 millisecond, 270. So it went down a little bit, but not so much. Because still, the other operations are still, so you always need to compare. Appending to a list, yeah, is not super fast, but relatively speaking, compared to other Python operation, it's pretty fast. Okay, so 10% improvement. This cannot be further vectorized because for each element, we need to know the values of the element before. So we cannot do it as a vector operation between NumPy arrays. We still need to have this loop. And when we hit this point, then we need to abandon Python and delve into other optimization techniques that are, for example, using Numba. Numba is really cool because it's super easy to use. You import it, and then you wrap a function inside like this. This is another way to use a generator. So you wrap your function or you process tree with the Numba JIT. You do it, and it works. I don't know why it works. It was giving an error before. So I put, this was the error I was getting before because of the memory view. I was getting an error because of the memory view. Okay, now it works, and let's benchmark it. 35 milliseconds. So from 250, we went to 35 because we are, Numba is a just-in-time compiler. So it just disassembles the, just interprets the code and creates very fast bytecode in LLVM virtual machine. So you need to install LLVM that is not a small package. That's the compromise. Another option that is similar is using Cython. You need to enable with this extension, and then it's more complicated. You need to add some boilerplate here, and then you need to define the type of the variable. Actually, you don't need to define it, but if you don't declare the type, you don't gain any speed. So that's the first run without declaring any type, just to see if it works. Because when I run this function is compiled, and if compilation went through, you don't get any error. And you also get this nice graphical representation of the execution. So it's all yellow, and it means that it's slow because it's using Python code inside Cython. So here I actually define the types. For index variables, I need to use pie size I. And for arrays, I need to use, these are floating point, float 64. I need to use double, that's the syntax. Just do copy and paste. But you define the variables like that. And the result is a function that has much less yellow, so it will be faster. And then the third one, I do the maximum optimization you can do in Python, in Cython, that is declaring all the variables and adding also these decorators that remove any safety check. These are safety check for out of bound access of an array or wraparound if you want to use, if you use negative index or if you go outside of the array, it will crash. You have a segmentation fault. So don't do it usually. And we will see that this will not gain much performance anyway. So it's just to see what you can do. So, okay, let's test. First, these 3 lines say that all the 3 functions give the same result. And then benchmark, execution time of the 3 functions. Okay, this is super slow because it became slower than the Python version. But now we have 35 milliseconds and 36 milliseconds for the other 2 optimized Cython versions. So we reach the same speed as Numba. The advantage is that it's, you can package a precompiled code in a wheel package or in a conda package, so your user will not need to install any compiler, which is hard. So for us it's hard because we develop it, but the user doesn't need it. In case of Numba, the user needs to install Numba and the dependency, so it's a larger download. Yeah. No, you generate a different compiled. So either you do manually or you use CondaForge. Basically, you just have your Conda recipe, and this amazing infrastructure they builds packages for Linux, Mac, and Windows. And this is what I do with my packages. I don't have a Windows machine, but they generate the Windows package for me. And it's pretty cool. Okay, this is a Cython reference. The last thing, but let's look only at the random number line. So far, we have timed these 3 lines. And one of these is generating random numbers. The other one is computing the process. Only the random part is 32 milliseconds. So actually, most of the time now is spent generating these random numbers. Our function became really negligible. So what can we do about it? With NumPy, nothing. But yeah, these are additional timings. We can use another module that is called, another package that is called the random gen. This is the future of NumPy random number generators. Is as an API that is compatible with NumPy, even though it includes more advanced algorithms that are faster and also more accurate statistically. So right now you need to install it with pip though. So let's see what happens. I import a random gen, and I want to see a benchmark, so I generate 10 million numbers, first with NumPy, and then with random gen. 300 millisecond NumPy, not bad. And 124 millisecond with random gen. So there is already a factor of 3. And on Linux is usually a little bit more than that. So this is really cool. In the future, we will have a faster NumPy, but right now, if we need it, we can use random gen. Okay, so we can do all the benchmarks and see to finish how much improvement we got compared to the first version. Remember that I was saving this variable because I wanted the number of the first time it. Bottom line, we get around 300 times improvement in speed compared to the first naive implementation. And another neat trick is that we can profile even the Cython code line by line. Let's see the result. Okay, 289, around 300 times faster. Oh, good. Do you use Linux? Oh, okay, so on Linux even more. Yeah, that's good to know. Okay, the cool thing about Cython, NumPy is cool and it's super easy to use, but when it optimizes something or it doesn't optimize something, you cannot do much about it. Instead, with the Cython, you can understand what's going on and see which part is not optimized. You can even run the line profiler, as we did before, on the Cython code. But for some reason, it doesn't work right now if I write the Cython code here. But it works if I put the Cython code in a separate file. So to put the Cython code in a separate file, the process is just copy the cell in a file that is called the ouprocess.pyx. I already did it for you. I'm just showing the file. And then create a setup.py file to compile the Cython code. You don't have to do this when you are in the notebook, but outside the notebook, you have to. So you need to use all this boilerplate just to build it. But you copy and paste. You just do it once and then you copy paste. And then you build the Cython code. You compile it to a shared library with Python setup buildx -- in place. And then you can import it. You import it as a normal Python module, and it will be fast as the one defined in the notebook. But the problem is that it's very hard to reload Cython code that you import. So you need to restart the kernel. So that's the compromise. But the advantage is that now the line profiling works. So you can actually see line profiler as before, but for Cython. So you have like a breakdown line by line to see where all the time is spent. And actually all the time is spent computing this line, because we computed 1 million times and instead all the other one. Okay, and for parallelization, I have just another small notebook that we will not have time, I guess, to go through because the time is over. But you can have a look by yourself. The trick is just use joblib. It's the easiest way, in my experience, to parallelize a scientific code. It has a simplified API. So what I did here is continuing this process of optimizing it. I copied the optimized function both in Cython and in Numba, and then I try to parallelize them. So joblib, you use it like that. It has this function, parallel and delayed, and it's basically mapping a list compression and transforming in a generator expression. So you first, let's say that our function is this one. In this case, it's computing in the square root, but can be the Ornstein-Uhlenbeck process. Maybe we want to do the simulation many times because we are fitting the parameters. So in this case, we can do many simulations in parallel like that with a list compression. With a list compression, we'll do it sequentially. This is normal Python, right? But then we just transform this list compression in this way. So everything that is inside the list now is inside this parallel and jobs. And jobs is how many parallel jobs you use. And the function itself, you wrap it in this with delayed. So the cool thing about joblib is that you can use both processes or threads just with a keyword. By default, there are processes, and if you put the keyword prefer threads like this, you will use threads. And this is advantageous because in processes, you need to copy the array to the other process. Normally, you don't share the memory. Even there are methods to share the memory. You can use all the calls. You say only if the functions that you call release the GIL, the global interpret lock. And most NumPy functions do release the GIL, so you will gain performances. And here in this notebook, we release the GIL. So the only modification that I did to the Cython function is adding this context, this syntax, no GIL, that is a way to release the GIL. And for the Numba version, I add the no GIL equal true, that also release the GIL. And so we gain the ability to run them in parallel with threads. So what I've seen when I was preparing the notebook is that if we use processes, we don't gain anything. It's even slower. But if we use threads, we actually have a factor of 2 improvement on my laptop that has 2 cores. So it seems to work. And at the end of the notebook, you see another example of not using joblib, but using the standard library threading on multiprocessing, actually. And this is the example. As you can see, in joblib was 1 line. In multi-threading is this bunch of lines. So it's much more complicated. So you will have more control, of course, but most of the time it's not worth it. And it's only for processes. If you want to use threading, it's even worse because multiprocessing has a simplified API in the standard library. But threading of the standard library has a lower level interface. So if you want to use threads that will give us the better performance, will be even more complex. So the lesson is joblib rules. Okay, thank you. If there are any questions, feel free to ask. The GIL is the global interpreted lock, is one of the cores of Python. It's an implementation detail that they, it's an implementation detail that they use to implement C Python. So the standard Python implementation is called the C Python, and basically the resources use a global lock. But the result of this is that you cannot run code in parallel because of this design constraint. It's not a theoretical constraint, it's just because C Python is implemented like that. But, so this apparently, I'm not expert about it, but what I read is that simplify drastically the code, so writing C Python, but it has this performance issue. Many people in the past have tried to do a version of C Python that removes the GIL, and these are super smart people, and no one succeeds so far. It's very, very complex to create a version of C Python without the GIL. But the other implementation like PyPy that are from scratch, so they don't use the GIL at all. Yes?
What is your experience about CUDA, and do you know any attempt to replicate something like NumPy and CUDA in Python?
So I don't have direct experience with CUDA, but what I know is that first you need the proper hardware, which I don't have. But I've seen that in Numba as supports CUDA. So in principle, what they say, and there is no reason why it should not be true, is that you just add another keyword to your decorator, Numba Git. I don't remember what's the keyword, like use GPU or something like that. Like we add this keyword here to release the GIL. You add another keyword there, and you run your code on the GPU. There will be constraints, of course. Not any code will run.
Look at CuPy. It's a NumPy basically on CUDA. So that can be a drop-in replacement for NumPy.
Yeah.
CuPy. C-U-P-Y.
Okay. Thank you for mentioning CuPy, CUDAPy, CuPy. That is a NumPy replacement that runs on CUDA. Uh, yeah, you can do this macro optimization. So multiply the array and norm times diffuse once outside of the loop. And then, yeah, you're absolutely correct. You will gain some. Not in Python though. In pure Python you will gain. In Python you will not gain.
No, perché bastava programmare tutte le cifre from scratch. Però se arrivato a una performance probabile con un C scritto in mezzo. Secondo me con un C scritto come è scritto su Python all'inizio. Eh sì, no, esatto, poi